Hello, in this course we have introduced probability theory. Based on a probability space, we defined one random variable, then two random variables, joint distribution of two random variables. Also, in the first part of this course, in probability theory, we defined conditional probability. So, using the concept of conditional probability, that was probability of A given B equal to probability of A intersection B divided by probability of B, we saw that this is a probability measure. So therefore, if you have two random variables, using these random variables, we can define different events and evaluate these conditional probability. So this gives us new distributions. We call them conditional distributions. So in this video, we aim to define various conditional distributions, as these conditional distributions will allow you to do estimation, detection, reliability. There are lots of application. So an important portion of application of this course arises from the conditions. For instance, you may know the output of a channel. Let's say output of a channel is Y, but you don't know what is X. So you know that you want to know the distribution of the input or the distribution of transmitted signal given the knowledge of that. So we want to know a conditional distribution of the transmitted signal, which we don't know, provided some measurement. So basically, conditional distribution is same as what we had in conditional probability. For instance, if we say the conditional distribution of two random variables given one event, so this means that the CDF, because we know that CDF is probability, is going to be probability that random variable Z is smaller than Z. This is smaller than this one, this is smaller than this one, and given these conditions. So this is going to be like that. And then this condition becomes intersection and then divided by probability of conditions. So this is coming from probability of, let's say, A given M, which is equal to probability of A intersection M divided by probability of M. And here event A is basically the event that Z is smaller than or equal Z, intersection with W, oh sorry, this is Z, smaller than or equal to real W. So all the conditional distributions are derived from an equation like that. But in different examples, these Z, W, or M, they can vary from each other. For example, if I let event M to be X is smaller than or equal X, and then instead of random variable Z and W, I have only random variable W, I will get this one. So I will get probability of the intersection of these and these, which is this is smaller than these and these, divided by that. Basically, this is equal to the CDF, the joint CDF of X and Y at point XY, divided by the marginal distribution of X, Y of X. And remember that this guy is equal to Fxy of X and Y, and Fxy of X and plus infinity. So if you replace this Y by infinity, you get the denominator. So if you take partial derivatives from this equation with respect to Y, then you get the conditional PDF of Y, provided that we know X is smaller than or equal X. So if you calculate the derivative, so both numerator of these functions, so I have to calculate d to dx of this function, which I will get becomes the derivative of these times these minus derivative of these times these. So if you calculate that, you get this expression. So you have to, because this is a PDF of y, so therefore you have to calculate derivative with respect to y, not with respect to x. So we get this expression. So this function, if this is a joint CDF, is a valid PDF for y for any given x. Another example, suppose that event M to be the event that x falls in between two real numbers. In that case, we can write the joint distribution of x and y. This guy is the event that x is smaller than x and y is smaller than or equal y. So this is one event and this is another event. X is between that. So if you write this expression, you will get this equation. Now we could, because this is this probability here, it says that, of course, y is in this area. Y is in this area, but x is bigger than, smaller than is x and is between. So I have to draw a line for x, and therefore I have three numbers. Let's say this is x1 and this is x2. So the random variable x shall be in this area. Okay, but I have another variable x here, and this x, I don't know where is it. It could be here, this x could be here, or it could be somewhere in between, or it could be somewhere here. So I have three cases, case 1, case 2, and case 3. Okay, so this expression of this property has three cases. Either x is smaller than or equal x1, or x is bigger than s1 and smaller than x2, or x is bigger than x2. Okay, so if this x is bigger than x2, the first event, this one, this event says that you need to be in this area. So now the intersection of this event and these events will become just this one. So in this case, that x is bigger than in case 3. In case 3, so you will have probability that x is bigger than x1 and is smaller than or equal x2, and y is smaller than or equal y, divided by probability that x is smaller than or equal x2 and bigger than x1. Now, if I consider, for example, case 1, in case 1, this event, this blue event, will become this area. And the intersection of the blue and yellow is empty. So what I will get probability of intersection of this one and this one will become empty. And then I have comma, y is smaller than y. So intersection of empty is 0. So divided by whatever, the result is 0. And in case 2, the intersection in case 2, intersection will be probability that x is bigger than x1, but is smaller, instead of x2 is smaller than x, and y is smaller than y, and then divided by probability of x being between x1 and x2. Okay, so in these three cases, we have to step by step write them and make sure that we don't make mistake, and write the expression and then simplify them. So this is for case 1, case 2, and case 3. Now, in each case, you substitute using the joint CDF, and you find these expressions. So this is the joint conditional distribution of these two random variables, provided we know that one of them is in a certain range. Now, if you take partial derivatives with respect to both n, x, and y, you get the conditional PDF of these, provided that you know that x, one of the random variables, in a certain range. So you will, for the first case, this is 0. This case gives you partial derivatives, and this case if you calculate the derivative with respect to x, you don't see any factor of x, so this becomes also 0. So only this case has non-zero. So if x is interval x1 and x2, the joint PDF, the joint conditional PDF is not 0, otherwise it's 0. Now what I see here is that the conditional PDF given this event is same as the conditional PDF divided by this number. The reason is that the only thing you know is that your random variable x is in this area. So the PDF outside of this area is 0. It's obvious. And the PDF inside this area is same as the PDF as before without the condition. The only thing is that you have a normalization factor to make the totaling. This is a normalization factor. This is a probability that x is between x1 and x2. And this is the normalization, so that the integral of the whole function becomes 1, so that this becomes a valid joint PDF. Now, in this example, I want to let if x1 tends to x2 and see what will happen.